Hello everyone. In this video, my plan is to quickly introduce the operation of a metal oxide semiconductor or a MOS transistor, metal oxide semiconductor transistor. And hopefully by the end of this video, you can start using these you can start analyzing circuits that include such transistors in them. So the reason that they're called a MOS or metal oxide semiconductor comes from the physical operation of the device and how it's actually fabricated. This is a cross-section, simplified cross-section of the device. So this is a silicon substrate or your semiconductor substrate right here. So usually silicon, and the silicon could be lightly doped with boron or basically phosphorus or n-type dopants. In the case of an NMOS or n-type MOS transistor, the substrate is doped lightly p-type with boron, and then there are two areas of highly n-type doped regions and that behave very much like conductors, and in between the two the p-type creates a barrier, and this is called the channel, and then above the channel there is a dielectric, typically made of silicon dioxide, on top of which there is a layer of metal or a conductor for that matter. And therefore, if you look at this specific region of the device, or generally the overall body of the device, you can identify a metal or a conductor that is on top of a semiconductor, and in between there is an oxide layer, and therefore the name metal oxide semiconductor transistor. MOS transistors are actually a type of the general field effect transistor category. You can actually fabricate other kinds of field effect transistors or FET transistors, and MOS is one of them. The reason these transistors are called field effect transistors is that the operation depends on the effect of an electric field that you create within the semiconductor. Now, to quickly understand the physics of the operation, you can imagine that these two regions that are highly n-type doped are two conductors, and in between them you have a region that is basically not conductive. Now, you can control the conductivity of the region in between, which generally in the case of a MOS is called the channel, through the application of a voltage on the gate that changes the conductivity through basically the effect of the electric field that you create between that gate and the semiconductor. So generally speaking, a MOS transistor is actually a four-terminal device. You have the metal on top of the semiconductor that is called the gate. You have two regions on the two sides. One is called drain and the other one is called source. And for the most part, which one is called drain and which one is called the source is not coming from the physical appearance. Basically, the device is symmetric. You can actually pick any one of the two as the drain or the source. And the fourth terminal is the substrate itself that is called the body terminal. Now, with what I explained to you, the reason this terminal is called gate is that whether or not you get current going from the drain to source depends on what voltage you apply to the gate. So this terminal actually kind of behaves like a gate for the current to go between the drain and the source. So this is very much like a switch, and whether or not current passes through drain and the source, obviously depends on the voltage that whether or not you apply a voltage between the drain and the source. But on top of that, you actually have a control voltage connected to the gate that also controls the current, and through the effect of manipulating the conductivity of the semiconductor or the channel that is in between the drain and the source. So you can actually the operation could be discussed in a lot more detail, and the physics of the operation is important and pretty interesting. But at this point, in order to prepare you for circuit analysis using these devices, you really don't need to know more, and we can quickly introduce the equation that describes the operation of the device and then move on to the circuit analysis. So for first of all, the symbol that could be used for the transistor is basically coming from this structure. So I'm going to start by drawing the symbol similar to what we have here. So this is your gate. These are the drain and the source. And generally the body terminal actually is shown with something like this right in the middle. Now, if you take the body terminal and connect it to one of these two, then the drain source at that point is fixed. In other words, the symmetry breaks down if you take the body terminal and connect it to one of the two, and the terminal to which you connect the body to for an NMOS transistor, which is the one that I'm showing right here, would be the source. So if I connect this to the terminal to the left, then that is always the source and the other one is the drain. And you can actually see the similarity between the symbol that is used and what's actually here. This shows you the capacitor and also tells you something very important, and that's the fact that the gate actually does not generally draw any current because it's not electrically connected to the rest of the device, and rather through this capacitance it only controls the current that passes through drain and the source. So with that, if I look at the voltage, current voltage or IV curve of the device, I have to be mindful of the fact that as opposed to the earlier devices that normally had two terminals, since we have more than two terminals, we actually have four, but then we can connect the body to one of the two and turn it into three terminal. Therefore, with the three terminal, I can't just show the performance or operation of a device using a simple IV curve. I actually have to have basically a 3D plot where I show more than only the voltage of two terminals and current that passes through those terminals. In other words, I need to show the voltage of between the drain and the source, then show you the current that passes through the drain and the source, but on top of that I have to at least have another one that shows the voltage between gate and the source. But if I don't want to do that and don't complicate it, I can actually put the voltage current relationship for the drain source in a 2D plot, but then draw the same plot for different values of gate source voltage, or the voltage between gate and substrate. Now, since we connected source to the body, then gate, the voltage between gate and the semiconductor is the same as the voltage between gate and the source. And in this specific case of an N-type, the voltage of the drain has to be connected to a potential higher than the terminal. Drain has to be connected to a potential higher than the source, and the current goes from the drain toward the source. Given the voltage of the drain is higher than the voltage of the source. Now, what you can see here is that obviously as the voltage of the drain increases with respect to the voltage of the source, and by the way, let me clarified that when we say VDS or VAB for that matter, we mean VD minus Vs. In other words, the potential of the drain subtracted from the potential of the source, or in other words, the voltage difference between the drain and the source. And when we say IDS, we mean the current that goes from the drain to the source. So obviously, VDS being positive means that the voltage of the drain is greater than the voltage of the source. Now, as you can see, as the voltage of the drain increases with respect to the source, the current increases. But then, for that to happen, you actually have to have the proper gate source voltage. In other words, you have to have proper voltage of the gate that guarantees that the conductivity of the channel reduces to an extent that the current actually passes through. And that voltage for an NMOS has to be a positive voltage. Given that, if you start applying any voltage that is positive, you start getting a current. So if you apply a drain source voltage that is positive, and assuming that you start applying also a positive gate source voltage, once the voltage of the gate source goes above the a threshold voltage that is called Vt, then the current starts flowing, and at that point the equation that describes the current that is passing through the drain source could be described in one of these two ways. In other words, if you look at this function, we have a portion of this function that to a great extent could be considered linear, and then there's a first portion that is quite nonlinear with respect to VDS. And that's what you see in between the two. The first part, the equation on the first row, is actually a nonlinear function of VDS. You can clearly see that there is a VDS to the power of 2 in there. But the second equation is actually a linear function of VDS. Now, obviously, there are quite a lot of other voltages and constants that needs to be discussed, but simply we are dividing the operation or the plot that describes the current of the drain source as a function of the drain source into two sections, and using two different equations to describe how the device behaves. Now, for the range that the gate source voltage minus the threshold voltage is actually greater than the voltage drain source, the device is operating right here in this region. And once the VDS starts becoming greater than VGS minus VT, we enter the second region. This second region is actually called the saturation region, and the first region is called the triode region. These are just names that are used for these two conventionally. Now, there are certain constants that are used here. Kn is actually a constant that comes from the physics or the properties of the material that is used in fabrication of the device. So Kn is equal to mu n epsilon oxide divided by 2 times thickness of the oxide times width of the channel over the length of the channel. Now, the length of the channel is pretty much what you see here between the drain and the source, and the width of the channel is the third dimension here that you can't actually see. Mu n is the mobility of electron, mu ox is the dielectric constant of the oxide that is used as the dielectric here between the gate and the semiconductor, and Tox is the thickness of this oxide right here. And as we explained, Vt is a threshold voltage that below which the channel could still be considered completely off and the device is not turned on. Obviously, this is the operation is not on off. So even at voltages smaller than threshold voltage, there are a certain amount of small amount of current that is passing. But for the most part, we can ignore that and assume that as long as the VGS is smaller than VT, you don't get any current passing through the drain source. And as soon as VGS goes above the threshold voltage, then you're dealing with one of these two situations. You're either in the triode region, and this is the equation that you're going to use, or you assume you're in saturation region, and this is the equation that you're going to use. Now, the last parameter that I need to describe to you is this lambda, which basically tells you what the slope of this line is once the device enters the saturation region. With that, I'm going to conclude this video. We're going to talk about how to use these transistors in simple circuits next. If you're interested to know more about physics of this device, I definitely encourage you to read books on semiconductor physics. Thank you very much.